Hey, what's up guys? My name is Ben K. Today let's talk about how do we create new models in OpenModelica. We will go through a modeling practice today. So in my other videos, we covered the important Modelica classes like connector, record, block, function, or model. So today we will use some of them to do this modeling practice. Here I prepared a real-world example, thermal convection, that we're going to model here. So on my left side is the example. So in order to have thermal convection to happen, that it must satisfy two conditions. One, we had a external surface, solid surface. Another one have like ambient air. Because there is a temperature difference between the ambient air and the external surface, and so there is a thermal convection effect going on here. So on my right side, I abstract this real-world example into a mathematical model. So basically for the wall, it's basically just a thermal capacitance. It satisfies the equation Cp times the relative of the temperature equal to the heat flux. On the right side O is the ambient air, so I assume that the temperature is constant. So in the middle is the heat in the thermal convection. For thermal convection, basically it's follow the thermal convection law, HA delta T equal to the Q. So we also need to have another subcomponent that like a heat port, or I call the heat flux, because we have to have the heat flux to transfer from the wall to the thermal convection, then from thermal convection to the ambient air. So next, let's go to the OpenModelica to do this modeling development. Okay, here I open my OpenModelica. If you don't know where and how to install OpenModelica, please check my other videos. A quick review here. On the bottom right corner, we have 4 tabs: Welcome tab, Modeling tab, Plotting tab, Debugging tab. So we are going to use Modeling tab here mainly, because Modelica modeling is a hierarchical modeling approach. So first we need to create a container or package to put all the models within there. So first let's go to the top left corner, new Modelica class. So we pick up the package. A quick review here, you can see that because the OpenModelica already provides options for the Modelica classes like function, block, record, connector, class, model. So we pick up the package, we name it, say Benki example text. Because in this example, I'm going to show you how do we do the modeling development through the text layer. Okay. So here we finish the package. So within this package, we're going to do the subcomponent. Okay. So let's go with the new Modelica class. So first we start with the connector. The connector is the connection between each two components, like the wall and thermal convection. So I'm naming it like heat part, because we are doing energy modeling. So we need a heat part. So I want to make it partial because I want to make it as a mother connector, so the child connector can inherit from the heat part. Okay, let's double click the heat part. So let's go to the text layer. A quick review here. For each model, there are about 4 representations. One is called icon view. So that's basically an icon. The icon will be shown here, the identifier for the heat part. Another one is diagram layer, which shows the model, the diagram for the model. And text layer. Text layer really show actually the equation behind to drive the physical law. And the information layer mainly is for like some like introduction or background for this model. So today in our modeling, we will mainly use the text layer. Okay. So in my other videos, we talked about a connector. There are 2 types of variables. One is called a potential variable. So I have to like lay out them here. Another one is called a flow variable. The difference between potential variable and the flow variable is because there is a potential difference which is cause something to flow. For example, if there is a voltage difference, this is also the reason why there is an electrical current flow in the electrical field. The same thing for energy field. Because there is a temperature difference, that's why there is energy flow. Okay, first let's define the potential variable. Say Modelica dot SI unit dot temperature. I will say unit equal to K. I will name it T. Okay. The next one we want to define the flow variables. Modelica dot SI unit dot heat flow rate called Q. Unit equal to watt. Okay, next let's check the connector very quick to see if there are any major issues here. Unit K. Okay, let me put the unit here. Unit equal to watt. Let's double check it. Okay, it's good. Okay. So let's save the model here. Okay, next I would like to create a child heat part to extend from the mother heat part. Heat part A. I want to inheritance from the mother part, heat part. Because the keyword in Modelica is extend for the inheritance. So that's my heat part A. I want to create another heat part called heat part B. Oh, I need to change the types. I need to delete that one. So I want to create this as a connector called heat part B. I want to save it. Save it. Let's check it. Let's check it. Okay, the reason I need to have two heat ports, A and B, is because the heat flux. For example, there is an inlet port that for the heat flux to come in to my component. There is another port I want to deliver the heat part out, deliver the heat flux out to another component. So that's why I need to have two heat ports. So the inheritance in Modelica is very similar to other programming language, like a OOP language, like a C++ or like a Python. So basically, when something extends from another, like the child head part, inheritance from the mother head part, it will inherit all this stuff from in the manifold, like the flow variables, potential variable, T and Q. So that is a very important point to pay attention. Okay, next, let's do our wall modeling. So my wall is really a model, so I'll just name it wall. So for my wall model, actually it is a thermal capacitance model here. So also like the equation is Cp times the derivative of the temperature is equal to Q. Okay, then I will define those parameters Modelica dot SI unit dot heat as is Cp. Okay. Unit equal to, okay, then because for the wall I need to have some initial temperature. SI unit dot temperature T0 and equal to K. So for the equation part, and we have Cp times. Now before I do that, I also need another component, heat part B node, because I need to have a node to connect it with the other components for the heat flux. So I rename it called a node. So because my node carried my flow variables and my potential variables, because my node is a heat part. My heat part is defined here. It has potential variables temperature, flow variables Q. So my equation will be node dot T derivative equal to node dot Q. Okay. So I also need to have an initial equation that for the initial condition here, say node dot T equal to my T0. This is my boundary condition. So finish this model. Let's check this model here. Okay, so we don't have major issues here. So next, let's create our model for ambient. Ambient, it is a constant temperature model. Okay, T equal to T constant. Okay, so because for the ambient, I need to have inlet part to connect with the other components. Like for example, I need to have heat part A, that's because I need to have inlet. And because of my constant temperature, so I need another parameter called Modelica dot SI unit dot temperature T ambient unit equal to K. Okay. So my node, because my node carried the potential variable and the flow variables, node dot T is my flow variable is equal to T ambient. Let's double check this model here. Okay, we're good. The next, let's make our model for the convection. So it follow the heat convection law, say H times A times delta, I would say dt equal to Q. Okay. So Modelica dot SI unit dot coefficient of heat transfer H, Modelica dot SI unit dot error A. Okay, here's my equation part. So Okay, also I need to have, because I also need to have inlet part and outlet part to carry those heat flux. So I have heat part A, called the part called the node A. Also need a heat part B for node B. Okay, so node A for my inlet, node B for my outlet. So my equation will be H times A times dt. So dt, because the dt is from the temperature difference, so I have node B dot T minus node A dot T. Okay, so this is the temperature difference, because my temperature difference from node A and node B equal to the heat flux, say node A dot Q. Okay. Because at the energy consumption, my node B dot Q equal to minus node A dot Q. Okay, so let's check the model here. Okay, so there is no major issue here. So right now we finish all our components. We have heat part, we have wall, we have ambient, we have convection. Next, let's hook up them together into a complete model. We call it cooling. Okay. Because my first component is wall. So I say wall. For the wall, I need to pass some parameters. Here is the CP and the T0. CP equal to 1.2, for example, T0 equal to, okay. Next is our convection part. Convection. For my convection, I need to have H equal to 1.5, A equal to 200. I think that's it. Because my convection part, yeah, have H and A. Next, I need to have my ambient can be. For my ambient, I just have a constant temperature called T. Let me double check. T ambient. Okay, T ambient equal to, say, okay, let's give a number here. Okay, here's my component. So next, the equation part, because I need to connect them here in the equation section. Say connect my wall dot node and the convection dot node A, because my wall, I want to connect my wall node to the inlet node or the thermal convection. Then my thermal convection outlet node to connect the inlet node to the ambient air. Then another one is connect convection dot node B and the ambient dot node. Okay, let's double check. Okay, finally, this is our complete model that is a balanced model, because we have 13 equations and 13 variables. So that's a good sign. So next, let's go and run the model. Let me go to simulation and do some simulation setup. Starting time, stop time, and the solver, and all other I will keep the default. So first, it will compile the model for us. So it might take a couple of seconds to finish the compilation. Okay, we finished the simulation here. So okay, when the simulation is finished, all the components in your model will be listed here, for example. Okay, your ambient, convection part, your wall part. So for the ambient, we give a constant temperature. And for the node, we carry the heat flux. For the convection part, we have node A and node B, the heat flux, temperature. The same thing for the wall. Okay, here is the result, the red line. Okay, I think we finished all this model development. But one last thing I want to double check is the instantiate model. For example, here, this tab. Actually, this, when you click that, it will put all your component models in your final model here for example, cooling. So as you can see that it's like aggregate all my input variables here in one model. So by that way, we have more clear idea that how my model will be looks like. For example, the wall equation part, and here is those defined parameters. Okay, so okay, thank you so much. Hopefully this video can be helpful for you.